Hello students, I am your mentor Dr. Surojit Mondal. In last few lectures, we have discussed the concept of electric field and how to calculate the electric field due to an electric dipole. Today, after this lecture, you will be able to solve problems on electric field and electric dipole. So we start with our first problem. The statement of problem 1 is 2 point charges QA is equal to plus 3 microcoulomb and QB is equal to minus 3 microcoulomb are located 20 centimeter apart in vacuum. So you have 2 point charges QA and QB QA is equal to plus 3 microcoulomb, QB is equal to minus 3 microcoulomb. The separation between them is 20 centimeters. Part A of this problem is what is the electric field at the midpoint O of the line AB joining the two charges. So first part is you have to consider the midpoint and then you have to calculate the electric field at the midpoint O between A and B. Okay. So you can see that AO is equal to BO is equal to 10 centimeters. So we may take note of it. QA is equal to 3 microcoulomb, that is 3 into 10 to the power minus 6 coulomb. QB is equal to minus 3 microcoulomb. So that is minus 3 into 10 to the power minus 6 coulomb. Then you have AO is equal to BO, that is equal to 10 centimeters. That is 10 into 10 to the power minus 2 meter. Okay. And in order to solve the problem, I need the value of 1 by 4 pi epsilon 0, that is 9 into 10 to the power 9 Newton meter square per coulomb square. If I want to calculate the electric field at point O, then I need to calculate the electric field produced at point O due to QA and QB separately. The electric field produced by QA at point O will be in this direction along OB, because you have to consider a unit positive charge at this point. It means that it will be a force of repulsion. So the magnitude of EA is 1 by 4 pi epsilon 0 QA by AO square. So that is equal to 9 into 10 to the power 9. QA is equal to 3 into 10 to the power minus 6 divided by AO is equal to 10 centimeters. That means 10 into 10 to the power minus 2 meter whole square. So you have 9 into 10 to the power 9 into 3 into 10 to the power minus 6 divided by 10 into 10 to the power minus 2 whole square. If you calculate this, it is 2.7 into 10 to the power 6 Newton per coulomb, and it acts along OB. Similarly, if you calculate the electric field produced at point O due to QB, it will again be directed along OB. Reason is, if we consider a unit positive charge at point O, it will be attracted by this QB charge. Okay, and the magnitude of EB is equal to 1 by 4 pi epsilon 0 QB divided by BO square, and if we consider the magnitude of QB, result is expected to be same as that of EA. So you have 9 into 10 to the power 9 into magnitude of QB as 3 into 10 to the power minus 6, BO 10 into 10 to the power minus 2 whole square. So again you expect the value to be equal to 2.7 into 10 to the power 6 Newton per coulomb, and it also acts along OB. So resultant electric field must be the algebraic sum of EA and B, and it will be directed along OB. So if we calculate the resultant electric field at O, then E is equal to EA plus EB, that is equal to 2.7 into 10 to the power 6 plus 2.7 into 10 to the power 6. So it is 5.4 into 10 to the power 6 Newton per coulomb. Okay, and as already mentioned, it will be acting along OB. So this is all about the first part of this problem. Okay. Now we are considering second part of the problem. The statement of the second part is, if a negative test charge of magnitude 1.5 into 10 to the power minus 9 coulomb is placed at this point, what is the force experienced by the test charge? So now you need to consider a test charge Q at point O, that is equal to minus 1.5 into 10 to the power minus 9 coulomb. Okay. So if we consider the force experienced by this Q charge, it is simply Q into E. So that is equal to minus 1.5 into 10 to the power minus 9, and resultant electric field at point O is already calculated. Okay. So that is 5.4 into 10 to the power 6. So 5.4 into 10 to the power 6, and if we simplify this, then it comes out as minus 8.1 into 10 to the power minus 3 Newton. This negative sign indicates that the force has a direction opposite to the electric field. So this force actually acts along OA. Okay. So you can see that the resultant electric field acts along OB as the charge has negative sign. So this will be acting in the opposite direction. Okay. Negative sign indicates that particular fact. I hope that you have understood this concept. Now we will solve problem number 2. The problem statement is 2 point charges 5 into 10 to the power minus 19 coulomb and 20 into 10 to the power minus 19 coulomb are separated by a distance of 2 meters. So you have 2 point charges. Say this is point A, this is point B. At point A you have 5 into 10 to the power minus 19 coulomb charge, and at point B you have 20 into 10 to the power minus 19 coulomb charge. These two charges are separated by 2 meters. Now the question is, at which point on the line joining them the electric field is 0? I consider that at point O the electric field is 0. This point O is at a distance x meters from A. Naturally, this point O is 2 minus x meter away from B. So first, you have to consider electric field at point O due to this and this charge. Okay? If we consider the electric field produced at O due to 5 into 10 to the power minus 19 coulomb, this will act along OB because this is force of repulsion, and let it be denoted by EA. So magnitude of EA is 1 by 4 pi epsilon 0 discharge divided by x square. So 5 into 10 to the power minus 19 divided by x square Newton per coulomb. The electric field produced at point O due to this charge will be along OA, because again this is a force of repulsion. Let it be EB. So the magnitude of EB is 1 by 4 pi epsilon 0 20 into 10 to the power minus 19 divided by this distance square. So 2 minus x whole square Newton per coulomb. So if you write the direction, A acts along OA and EB acts along OB. EA acts along OB and EB acts along OA. So in order for electric field to be 0 at point O, the magnitude of EA must be equal to magnitude of EB, so that they can cancel each other. They are already acting into opposite direction. So these two forces, these two electric fields must be equal and opposite. So I need to consider that the magnitude of EA must be equal to the magnitude of EB. So you have EA is equal to EB. Now you substitute the values. 1 by 4 pi epsilon 0, 5 into 10 to the power minus 19 divided by x square, that is equal to 1 by 4 pi epsilon 0 20 into 10 to the power minus 19 divided by 2 minus x whole square. So if you simplify this expression, so you can write it as 2 minus x whole square is equal to 4x square. Or you can write it as 2 minus x is equal to plus minus 2x. So you have two solutions for x. One is 2 minus x is equal to 2x, or you have 2 is equal to 3x, or x is equal to 2 by 3. The other solution for x is 2 minus x is equal to minus 2x. So you are getting 2 is equal to minus x, or x is equal to minus 2. What you get is two solutions for x as x is equal to 2 by 3 meter, or x is equal to minus 2 meter. This solution of x is equal to minus 2 meter is not possible, because x is equal to minus 2 meter indicates a point on the left hand side of A. As these two are positive charges, you cannot have electric field to be zero at any point on the left hand side of A or on the right hand side of B. If these two charges are positive, electric fields due to these two charges must be acting into opposite directions, which is not possible when we consider a point on the left hand side of A or on the right hand side of B. So x is equal to minus 2 meter is not possible. The solution is x is equal to 2 by 3 meter. So you can see that x is equal to 2 by 3 meter. Another interesting thing you may take note of. You can see x is equal to 2 by 3 meter is a point which is closer to A. Okay, this is obvious. If your numerator is greater, denominator must also be greater in this expression, so that this ratio must be equal to this ratio in order for these two magnitudes to be equal. And that is why while drawing I have deliberately chosen point O to be closer to A, not towards B. I believe that it is clear to you. Now we will solve problem number 3. The problem statement is 3 charges plus Q, minus 2Q and plus Q are located at the vertices of an equilateral triangle of side twice L. What is the equivalent dipole moment of the arrangement? So first, we need to draw the diagram. Okay, so I have drawn this diagram. You can see that I have considered three charges at three vertices of an equilateral triangle. At point A, I have considered minus 2q charge. At point B, I have considered plus q charge. And at point C, I have considered plus q charge. The length of each side of this equilateral triangle is twice L. Now you need to find out the equivalent dipole moment for this arrangement. So in order to understand this problem, or in order to solve this problem, I consider that I have 2 point charges minus q and minus q at point A. Then I can consider that there is a dipole which is acting from A to B. I have another dipole which acts between A and C, and it is directed from A to C. So I can consider one dipole with its dipole moment as P1 acting in this direction. And I have another dipole which acts along this. The corresponding dipole moment is P2. So one is acting from A to B and the other is acting between A and C, or it acts from A to C. It is an equilateral triangle, so this angle is also 60 degree. Other angles are also 60 degree as well. Okay. So we can write magnitude of P1 is equal to magnitude of P2, that is equal to any one of the two charges into separation between them. So Q into twice L. If I want to find out the resultant of these two, that is the equivalent dipole moment for this arrangement, I may consider components of P1 and P2 in the horizontal and vertical direction. Okay. So this appears to be the midpoint of BC. Okay. If we consider component of P1, then one component will be acting along this and the other component will be acting along this. This angle is now 30 degree. So you see that base by hypotenuse is equal to cos theta. So base is equal to hypotenuse into cos theta. So this component is P1 cos theta or cos 30 degree in this case. Similarly, perpendicular by hypotenuse is equal to sin theta. So perpendicular is equal to hypotenuse into sin theta. So this is equal to this. So this component is P1 sin 30 degree. Okay. Similarly, I may consider components of P2 in this horizontal and vertical direction. Okay. So as before, I expect this component to be P2 sin 30 degree, and this component will be P2 cos 30 degree. As evident from the figure, magnitude of P1 and P2 are the same. So P1 sin 30 and P2 sin 30 must be same in magnitude, and they are acting into opposite directions. So they will cancel each other. So the equivalent dipole moment of this arrangement should be sum of these two components, which is also acting along AO. So the magnitude of the resultant dipole moment, the magnitude of the resultant dipole moment, let it be P, must be equal to P1 cos 30 degree plus P2 cos 30 degree. So this is 2P1 cos 30 degree. We already know P1 is equal to P2 is equal to Q into twice L. So this is Q into twice L. Cos 30 degrees root 3 by 2. So if we simplify this, you will get 2 root 3 Q into L. So this is the magnitude of the equivalent dipole moment of this arrangement. And as you can see in the figure, this acts along AO. So this is how you can calculate the resultant dipole moment or equivalent dipole moment of some given arrangement. Okay. Now we will consider problem number 4. The problem statement is two charges plus 10 microcoulomb and minus 10 microcoulomb are placed 5 millimeter apart. Determine the electric field at a point P on the axis of the dipole 15 centimeter away from its center O on the side of the positive charge. So let us first draw this diagram. Actually, you have a dipole AB. The length of the dipole is 5 millimeters. You consider center of this dipole to be O, and you consider a point P on the axis of the dipole on the right hand side, that means on the same side of the positive charge. And this point P is at a distance 15 centimeters from the center of the dipole. We have already discussed the theory to calculate the electric field at an axial point P due to an electric dipole. So you can see that this electric field at point P will be act along OP. Okay. You can calculate this magnitude of EP by applying the actual formula. But you can also see that this separation is much less than this distance, or in other words, this R is much greater than this twice A. So I may consider the case where R is much greater than A. So under this consideration, the electric field at an axial point can be calculated by using this formula. EP is equal to 1 by 4 pi epsilon 0 2P by RQ. And we already know that P is equal to Q into twice N. Okay. Now you can substitute the value. 1 by 4 pi epsilon 0 is 9 into 10 to the power 9 into 2 Q. You consider any charge, magnitude of any charge. So 10 into 10 to the power minus 6 coulomb, because it is given in microcoulomb. Twice L, that is 5 millimeter. I need to convert this into meter. So 5 into 10 to the power minus 3 meter divided by R cube. R is equal to 15 centimeters. Again I need to consider meter. So I have 15 into 10 to the power minus 2 meter whole cube. Value of EP can be calculated from this. 9 into 10 to the power 9 into 2 into 10 into 10 to the power minus 6 as Q, then 5 into 10 to the power minus 3 as twice L divided by 15 into 10 to the power minus 2 whole cube. Okay. If you calculate this becomes 2.67 into 10 to the power 5 Newton per coulomb, and this acts along OP. So this is how you can calculate the electric field at an axial point of a dipole which is far away from the center of the dipole. This problem statement has second part. So now we will be considering the second part of this problem. So in the second part, you have same thing. That means you have same electric dipole. Separation between them is again 5 millimeters. Okay. But now you have to find out the electric field at a point Q 15 centimeter away from O on a line passing through O and normal to the axis of the dipole. So actually you need to consider some equatorial points. Okay. So this is also 15 centimeters as before. This point is Q point and you have to find out electric field at point Q. That means now you need to calculate the electric field at an equatorial point. So if you can remember the theory, this electric field will be acting Along this direction, if I consider this point to be A, this point to be B, then this electric field will be acting from B to A. And again we consider R to be much greater than A, because you can see 15 centimeter is much greater than 5 millimeters. So the magnitude for electric field at an equatorial point Q is 1 by 4 pi epsilon 0, then P by R cube. This is the formula. It acts along BA. 1 by 4 pi epsilon 0. P is equal to, as before, Q into twice L divided by R cube. So this value is 9 into 10 to the power 9. Q, you consider any magnitude of these two charges. So 10 into 10 to the power minus 6 coulomb. Then twice L, 5 millimeters. So this is to be converted into meters. So 10 to the power minus 3 to be multiplied with 5 divided by 15. So 15 into 10 to the power minus 2 meters. Okay, it's whole cube. So you have 9 into 10 to the power 9 into 10 into 10 to the power minus 6 into 5 into 10 to the power minus 3 divided by 15 into 10 to the power minus 2 whole cube. So you can calculate, or it is the value which will be just half of the previous value. No? Earlier you have calculated 2p by r cube. Now I am calculating p by r cube. So its value will be 1.33 into 10 to the power 5 Newton per coulomb. It acts along BA. So this is how you can solve any problem on electric dipole. Thank you.